Today we're going to cover the basics of Gaussian elimination. So suppose you wanted to solve x plus 2y is equal to 4 and 2x plus y is equal to 5. The way you do this is you want to get rid of this 2, and to do that you multiply the first equation by minus 2. So the x's will cancel. So when you do that, the first equation becomes minus 2x minus 4y is equal to minus 8. And the second equation stays the same. And then when you add the two equations, the x's cancel and the y's turn into minus 3y is equal to minus 3, which clearly says y is equal to 1. And then you go back and you plug y into the second equation, say, to get 2x plus 1 is equal to 5, which says that x is equal to 2. Okay, I assume everybody's familiar with this technique. And I'm going to do the standard thing of getting rid of the x's and y's and just writing this in an augmented matrix form. The 1, 2, 2, 1 are the coefficients of the original equation, and the 4, 5 are the right-hand side. And what I did is I took the first row and I left it, and then I added minus 2 times the first row to the second to turn this into this matrix. And I just stopped there and solved it, but another thing I could have done was continued, multiplied the second row by minus a third to turn this into this equation. And I could have even continued by adding a multiple of the second row to the first to kill that 2, which would turn the equation into 1, 0, 2, 0, 1, 1, which says that x is equal to 1 and y is equal to 2. So that's the sort of most complete version of Gaussian elimination, but usually you don't need to go all the way to the end like that. Now, the regular case of Gaussian elimination is the following. It's the square case, n by n, it's n equations and n unknowns. And it's the case when you can apply row operations and get to this form. You get to a matrix with non-zero entries on the diagonal and zeros below the diagonal. That's called the regular case, and here's an example. If you take this augmented matrix, you can use this 1 to kill the things below it. And this 1 is called a pivot. And you use it by multiplying the first row by minus 2 to kill that 2. So the first row stays. The second row gets a 0 in the first entry. And some other entries. And then you can multiply it by minus 3 to kill the 3 and get a 0 in the first column, and that takes care of the first column. And now you look at the second column and you can use this minus 5, that's the next pivot, and you can use that to kill everything below it. In this case you just add, you multiply by minus 1 and add it to the row below, so the first two rows stay the same. And the last row becomes 0, 0, minus 5, and now you're done. You've applied row operations, and you've got some non-zero entries on the diagonal, and this third one is also called a pivot, and all three pivots were non-zero. And now it's easy to go back and solve the equation. This is called back substitution because you start with the last variable z, and say minus 5z is equal to minus 5, which says z is equal to 1. And then the previous line says minus 5y plus z is equal to minus 9, and plugging in z is equal to 1 tells us that y is equal to 2. And then finally the top line says x plus 2y plus z is equal to 6. And if you plug in y and z, you conclude that x is equal to 1. So there's our solution. X, y, and z are 1, 2, and 1. Now, again, instead of doing back substitution, an essentially similar procedure is to do these operations going back. So, well, the first thing is to multiply the last row by minus a fifth to turn those pesky minus 5s into 1s. And then use that 1 to kill the number above it, and you get this. And then you multiply the second row by minus a fifth to get some 1s. And then finally you use the second two rows to kill the entries in the first row, and you finally wind up at this matrix to the left as the diagonal matrix, is the identity matrix, 1's down the diagonal, and you get 1, 2, 1. So again, that's more than is necessary, but it spells it all the way out, and you just get the solution in the right-hand column. Okay, so that illustrates that the regular case is exactly the case when all of the pivots are non-zero. So remember, the regular case is the case where we can reduce it to a diagonal matrix with non-zero entries, and you can do that exactly when all of the pivots are non-zero. Okay, so let's move on now and look at a matrix interpretation of this. And here's a very important observation. These row operations that we've been doing, adding a multiple of a row to another, is exactly the same thing as multiplying the given matrix on the left by another matrix. So this is a very important principle, so let's highlight it. Row operations are exactly the same thing as multiplying on the left. So let's look at a basic example. You have this matrix 1, 2, 2, 3, and a row operation of multiplying the first row by minus 2 and adding it to the second row gives you this. And that's just exactly the same thing as taking this given matrix, 1, 2, 2, 3, and multiplying it on the left by this matrix, 1's on the diagonal, 0's above, and minus 2. Because if you do this out, you get 1, 2, 0, minus 1. So that is, this matrix here is the one which is accomplishing this operation. So what this says is that the Gaussian elimination algorithm really, at least in the regular case, which is what we're talking about here, just amounts to taking your given matrix and multiplying it on the left by a matrix of this form, and then doing that again, and repeatedly multiplying it on the left by a lower triangular matrix, and after an n steps of this, after however many steps you need, you can turn it into an upper triangular matrix with non-zero entries down the diagonal, and I'll call that U. So every one of these matrices E, these are called elementary matrices, corresponds to a row operation. You do a sequence of row operations, and you turn A into an upper triangular matrix. And this sequence of row operations I'll call L, because when you multiply all of these matrices together, what you get is a lower triangular matrix. In other words, I have an equation of the following sort. I have a lower triangular matrix L, and I've multiplied it times my given matrix A, and the result is an upper triangular matrix. So this is a very important concept, and it's the sort of concise way of thinking of Gaussian elimination. So let's look at our previous example from this point of view. So I had this matrix, and I converted it to this matrix by a sequence of row operations, and I'm going to have this little the column vector on the right tag along for the ride. So here's what I did. I started with this matrix, and the first thing is I multiplied the first row by -2 and added it to the second, and that is exactly the same thing as multiplying on the left by this matrix. Okay, that's this -2. And then I multiplied the first row by -3, so that's multiplying on the left by this matrix. Okay, and the next thing I did is I multiplied the second row by -1 and added it to the third row, so that's this matrix. And after doing those three operations, what I got was the following matrix, this one right here, this U. And so the product of these three matrices here, which I'll call L, if you multiply them out, you just work that out, and what you get is this lower triangular matrix times A is this upper triangular matrix. And here at this last step, I've just dropped off the final vector, so I have just something about these 3x3 square matrices. So this is my LA is equal to U formula. Okay, so that's, again, that's the example that I did before, written out in this, thinking of it in terms of this LA is equal to U procedure, and there's my L and there's my U. So what I've done is I've taken a matrix A and I've multiplied it on the left by a matrix L to get an upper triangular matrix U. By multiplying both sides of this equation on the left by L inverse, I could write this instead as A is equal to L inverse U. And now L inverse is lower triangular and U is upper triangular. And now I just want to switch the roles of L and L inverse. This isn't serious. This is just sort of for notation's sake. And what I get is that I can write the matrix A in the form LU. This is called the LU decomposition of the given matrix A. So, and again, what that means is that I've written A as a lower triangular matrix times an upper triangular matrix. Now, in terms of an algorithm, it's easier to do it with the L on the other side, to start with A, do row operations to get U, and then at the end you somehow get the L to the other side. So let me explain what I mean by that. You find a bunch of these elementary matrices which you can multiply on the left, and then you move them to the right one at a time, and you switch the order and you switch them with their inverses. And you write A is equal to E1 inverse times E2 inverse down to EM inverse times U. And that's a very easy step to do, and it moves the L to the other side. So let's look at that in our previous example. Here I've written out our example. I've written A, multiplied it on the left by 3 lower triangular matrices to get U, and I want to show how you move everything to the other side. So the way this works is the following. Here's my matrix A, and the first thing that I do is, well, I'm going to just sort of put in some empty matrices here. I'm going to write A is equal to a product of 3 matrices times U, and the first thing I do is I take this very first matrix here and I put it in the last place, and I simply change the sign of the single entry below the diagonal. That's because for an elementary matrix like this, the inverse is just changing the sign on that one entry. And I do it to the next one. I take this next matrix here and I put it next, and I change the sign on the -3. And then finally I take my third matrix and I put it down here in the reverse order, and I change the -2 to a +2, and now I have 3 lower triangular matrices which I can multiply together to make my new L. And when I do that calculation, I conclude that my original matrix A is equal to the following lower triangular matrix that I get by multiplying these 3 together. That gives this matrix here. Turns out to be 2, 3, 1 times this matrix here. And so that is the A is equal to LU formula, the LU decomposition of the matrix A.